Hello everyone, welcome to this course where we will learn how to model datasets with linear regression using the Tidyverse packages in R. The Tidyverse package is one of the most popular packages used in data science to import, manipulate, and plot data. It is made up of several packages, each designed for different aspects of data analysis. The readr package can be used to read and write several types of files such as CSV files or TSV files. The tidyr package is used to tidy the data. The dplyr package is used to manipulate the data. And finally, ggplot2 is used for plotting. What do we mean by tidy data? In a tidy data, each variable must have its own column and each observation must have its own row. If you want to learn more about the Tidyverse packages, please let me know in the comment section and I will design a course for the Tidyverse ecosystem. The purpose of this course is to convey the concepts of data modeling. Although I am using R and Tidyverse packages, please understand that you can use the same concepts to model your data in other languages such as Python or even other softwares like GraphPad Prism. Now, let's get into the concepts of modeling. Before we begin, we need to install the Tidyverse package. To install the package, use the command install.packages, and then you can load the Tidyverse package by calling the command library and in brackets Tidyverse. Now, we are ready to start the course. Let's take an overview of what we will be learning today. In the first part, we will discuss the concepts of modeling. Then we will learn how to do a simple linear regression. Then we will move on to multiple linear regression and finally end with evaluating our models. Concepts of modeling. Modeling is regularly used in causal inference and statistical data analysis, and nowadays it is used in machine learning and training artificial intelligence. Let's look at a general modeling formula. In this formula, y is a function of x. Y is called the response variable and x is called an explanatory variable. Y is the variable you want to model and x is the variable you use to predict the values of y. F denotes a mathematical function that defines the relationship between y and x. F of x is called signal. E or epsilon is called the noise that represents the error in the model. In a perfect model, E becomes 0. This is one of the most important concepts in modeling. A good model has high signal to noise ratio. Today, we will be using the conifers dataset, which contains the height and girth of different types of conifer trees. You can find the link to the data in the description below. We will first import the data using the read_CSV function from the readr package. We will save it as conifers. Glimpse is another function from the dplyr package that is used to look at the contents of the data. Calling glimpse, we can see that the data has 3 columns and 10,000 observations. The data contains 3 variables: type, which contains the names of 4 different species of conifer trees, namely oak, maple, pine, and birch, their heights in feet, and their girths in feet. Looking at this data, we can ask the following question. Does height of a tree depend on its girth? Mathematically, we can ask, is height of trees a function of their girth? We can now classify our x and y variables. The response variable y becomes height and the explanatory variable x becomes girth. Before we start linear regression modeling, we need to do an exploratory data analysis. Exploratory data analysis, or EDA, can be typically divided into 3 steps. First, we want to understand our data. Second, we want to visualize our data using different types of plots. And third, we want to calculate some summary statistics of our data. These steps will give us high-level information of our data. The first step is understanding the data. This step we have already completed previously. We have seen that the conifers data contains 3 types of variables. Type contains 4 different species of conifer trees, namely oak, maple, pine, and birch, their heights in feet, and their girths in feet. Next, we visualize the data. To visualize the numeric variable heights with a categorical variable type, we can do a box plot. To make a box plot, we will use the ggplot2 package. Inside the ggplot function, we will add the conifers data along with the x variable type and y variable height inside the aesthetics or AES function. Then we will call the geom_boxplot function to make the box plot. On the right hand side, we can see the box plot. The line inside the box represents the median value. As we can see, the median value of height of birch trees are the highest and the median value of the oak trees are the lowest. Pause here and try to do the same for the girth variable. Another way to look at numeric data is to look at the distribution. To look at the distribution of numeric variables, we can plot a histogram. This can be done using the geom_histogram function in ggplot2, where we set x to the numeric variable we are interested in. Here, we look at the distribution of heights of all the trees. We see that the median height is around 10 feet. We can also see that there are very few trees with heights greater than 25 feet. Because the histogram is tailing towards the right, we can say that the height data is right skewed. Skewed data is problematic in modeling since the data is not distributed evenly. Since there are only few trees with heights over 25 feet, it will be hard to accurately predict the heights of medium to shorter trees, which represent most of the population. To fix it, we can log transform the x-axis scale. To change the x-axis from a linear scale to a log scale, we can add a function called scale_x_log10. As you can see that after log transformation, the data looks like a normal distribution. This will help us with accurate modeling. There are 2 things to remember when transforming data. First, in this case, log transformation is making the x-axis intervals multiplicative rather than additive. And second, axis transformation is not always helpful. So perform transformations with care. Pause the video here and see if girth data needs transformation as well. Here is the box plot for the girth variable. We just have to change the y inside the AES function of ggplot to girth_feet. After plotting the histogram of the girth data, it looks like it is also right skewed like the height data. Log transforming the girth data makes it closer to a normal distribution, and this will help us model our data accurately. In step 3, we will calculate the summary statistics such as mean, median, and standard deviation for the data. We will use the group_by function from the dplyr package to group our data by the type of tree and calculate the mean, median, and standard deviation inside the summarize function in dplyr. Like we saw previously in the box plots, the median heights of birch trees are the highest and that of the oak trees are the lowest. The standard deviation is a measure of how dispersed the data is in relation to the mean, and we can say that the heights of oak trees are clustered tightly around the mean compared to the heights of birch trees. Pause here and try to do the same for the girth variable. Likewise, we did the same for the girth data. Before we start linear regression, let's revisit the modeling framework once more. We saw that when y is a function of x, y and x are response and explanatory variables respectively. The term fx refers to the signal, and the term E or epsilon refers to the noise. In a perfect model, fx will be able to accurately predict the values of y given values of x. In our case, in the conifers data, based on the question we asked, the response variable is height and the explanatory variable is girth. To perform modeling, we need to know the values of the response variable and the explanatory variable. What is not known is the signal fx and the noise epsilon or E. Using the values of x and y, we want to find a function f hat as represented by a dash on top of f that captures the true function while ignoring epsilon or E. The fitted function f hat ideally should be able to accurately predict the value of y hat based on the values of x. In this case, if we want to know the value of girth of a tree, our fitted model should be able to predict the height of the tree. Previously, we were looking at one variable at a time, but not the relationship. In modeling, we will look at two or more variables simultaneously. One way to visualize a relationship between two or more numeric variables is by using a scatter plot. Let's visualize some correlation with scatter plots. Before we make the scatter plots, we need to add the log 10 height and the log 10 girth data to our conifers dataset. We'll use the mutate function from the dplyr package to add them to our conifers dataset. We will be using the geom_point function from the ggplot2 package to visualize the log height and log girth values. Looking at the plot on the right, we might ask, what is the relationship between height and girth? Does increase in girth causes an increase in height or a decrease in height? To determine whether the relationship between two variables are positive or negative, we need to find out their correlation coefficient. A correlation coefficient is a numerical measure to determine a statistical relationship between two variables. The value of the correlation coefficient is always between -1 and +1. When the correlation coefficient is close to 1, it means that the variables are positively correlated, where an increase in x leads to an increase in y. When correlation coefficient is close to -1, it means negative correlation, where an increase in x causes a decrease in y. When the correlation coefficient is close to 0, it means that the variables are not correlated at all. The correlation coefficient in R can be calculated using the core function. From the conifers dataset, we have used the $sign to extract the height and girth column and saved them as height and girth respectively. Running the core function with height and girth, we can see that the correlation coefficient is 0.64, which shows a positive correlation between the height and the girth values. This means that as girth increases, we expect the heights will increase as well. We can use a regression line to visualize correlation. By adding a geom_smooth function and calling the method lm, which stands for linear model, we will be able to visualize the regression line of this data. The SE or standard error equals false does not show the standard error regions in the plot. Previously, we had computed the correlation coefficient of 0.64, which indicated positive correlation between the height and the girth variables. The regression line is also consistent with the correlation coefficient. The function of the regression line is the linear model f hat that I had mentioned previously. Now we move on to the next part of the course, where we will see how to model a simple linear regression. In linear regression, the equation is always that of a straight line. As a result, our fitted function f hat of x can be represented as beta 0 plus beta 1 times x, where beta 0 is intercept and beta 1 is the slope of the line. Our final linear model equation thus becomes y hat equals to beta 0 plus beta 1 times x. Notice that the epsilon term was removed because in the ideal world, the fitted function f hat should only capture the signal and eliminate all noise. To compute the regression line of our data, we need to use the lm function in base R. Call the function lm and within it specify the formula y tilde x, where y is the response variable and x is the explanatory variable. In our case, log10 underscore height tilde log10 underscore girth. We also need to mention the data we are using, in this case, the conifers data. Let's save this in the conifer underscore model variable. When we print the conifer underscore model, it returns the lm object and its coefficients. The coefficients of the model is particularly important because it gives us the slope and the intercept of the linear regression line. The slope in this case is called as log10 underscore girth. The coefficients can be printed by calling the model object conifer model inside the coefficients function. When you run the coefficients function on a model object, it returns a vector of two values. The first value is always the intercept and the second value is always the slope. Let's look at what the slope and the intercept means. Before I explain the relevance of slope and intercept, let's first raise them to the power of 10 since they were log transform values. The intercept is the point on the y-axis where x is equals to 0. While mathematically intercept is relevant, in our case it is not. This is because it means that a tree with girth 0 will have some height, which is impossible. The slope, however, has a meaning. A slope of 1.84 means that for every unit increase in girth, there is a 1.84 feet increase in height of trees on average. Like the coefficients function prints the coefficients, which are the slope and the intercept of the model, there is another function called summary that prints the summary of the entire model. We have already looked at the call and coefficients before. The coefficients are printed here in a different way. Now the coefficient values are in the estimate column. The standard error and p-values are also printed for the individual coefficients. Later on, we will look at the meaning of residuals and other values such as residual standard error and r-squared values. One thing to note here is that the model summary output is not in a tidy format. In order to convert it into a tidy format, we need to use another package called broom. The package broom has functions that help summarize key information about models in tidy tables or data frames. Broom provides 3 verbs that can make it convenient to interact with model objects. The first one is tidy, which summarizes the information about model components. The second one is glance, that reports information about the entire model. And the third one is augment, that adds information about each observation to a dataset. We will use each of these functions later. Let's look at the tidy function in broom. The tidy function summarizes key information about the model components. Calling the tidy function on the conifer model, we can see that the slope and intercept are now arranged in a data frame. Their values are in the column estimate. Now it is time to make some predictions. Let's say we went into the field and measured the girth of a conifer tree to be 0.8 feet. Can we predict the height? To predict its height, we need to use our model's intercept and slope. Remember that we had log transformed both height and girth variables while running the lm function. So we first need to transform the girth of 0.8 feet using the log10 function. Then we will multiply its value with the slope 0.266 and add 1.04. Finally, when we get the height, we need to raise it to the power of 10, and that gives us the new predicted height of 10.33 feet. So using our model, we can predict that the height of a tree of girth 0.8 feet is 10.33 feet. Now let's say we went back to the same tree with girth of 0.8 and measured its height to be 19.9 feet. Therefore, we can see that our model has underpredicted the height of the tree to be 10.33 feet. It could have also been possible that our model had overpredicted the tree heights. This is the concept of residuals. Residuals can either have a positive value or a negative value. For each predicted response value, there is a residual. The augment function from the broom package prints the fitted values and the residuals for each observation in our data. These values can be found in the .fitted and .resid columns respectively. It also prints the hat values and the sigma values, which we will be looking later in the model evaluation section. There is another useful function in the broom package called glance, which prints the information about the entire model. We will be looking at some of these parameters later on in the model evaluation section. Now let's say we have gone back to the forest and measured the girths of several trees, and we want to predict all their heights. We can do this one by one simply by plugging the new values and the coefficients into our equation. But that will be tedious, and for thousands of data points, it will be impossible. R has a handy function called predict to help us compute multiple responses from a model object and new data that we have collected. First, we need to convert the girth data into a tibble or a data frame. Since we used log10 in our model, we need to log10 transform the girth data. Make sure that the column names are the same as the original data before you can start prediction. We can now use the predict function. Inside the predict function, you have to call the model element, in this case conifer_model, and the new data that contains the log10 girth of the trees that we want to predict the heights of. We can use the mutate function to add the predicted log10 height to the new data variable. Remember, since this is log10 height, we need to retransform it back to the height in feet. For that, we're going to raise the log10 height value to the power of 10. So this is the way that we can predict multiple values in R. In this part of the course, we learned how to run a simple linear regression using both numeric explanatory and response variable. In the next part, we will learn how to run a simple linear regression using a categorical explanatory variable and a numeric response variable. We're going to ask the question, does height depend on the type of tree? Notice that the explanatory variable type is a categorical variable that consists of 4 different types of conifer trees. And the response variable is height, which is numeric in nature. As with every modeling exercise, we will first perform an exploratory data analysis, which involves understanding the data, followed by visualization and summarizing the data. We have already gone through the step of understanding our data, and we know that there are 4 types of conifer trees, namely maple, birch, pine, and oak. The height data, as we have seen before, was right-skewed, and we have log transformed it to make it look like a normal distribution. To visualize categorical data, we can use a histogram using the geom_histogram function in the ggplot2 package. To separate the histograms based on the type of tree, we have to use the facet_wrap function, and inside we set the vars argument to type. We have also summarized the data by taking the mean, median, and standard deviation for each type of tree. We have grouped the data by type and used the summarize function from the dplyr package to get their mean, median, and standard deviation. We can see that the mean heights of birch trees is 22.3 feet, maple is 11.1 feet, and so on and so forth. Now we run the lm function. On the left hand side, we have the response variable log10_height, and on the right hand side, we have the explanatory variable type. We have set the data argument to conifers. We have saved the lm call to the conifer_model_2 variable. When we call the tidy function on the model object, we can see that it prints 4 coefficients. One of them is an intercept, and the rest are for the 3 different species of trees. The coefficients of birch is missing, but if we raise 1.30 to the power of 10, we get the mean height of birch trees. So what are the other coefficients? Let's take a closer look. The other coefficients are the mean log10 heights of maple, oak, and pine, and are calculated relative to the birch tree. For example, if we subtract 0.304 from the intercept 1.3, we get the mean log10 height of maple of 0.996. And if we raise it to the power of 10, we get the mean height of maple trees, which is 9.9 feet. We can simplify this by appending +0 at the end of the categorical variable type in our model. This specifies that all the coefficients should be relative to 0, and it makes the results easier to read. Now we can raise the coefficients to the power of 10 to get the mean heights of different types of conifer trees in our data. One thing to note is that this works well for simple linear regression. But if you have multiple categorical explanatory variable, it might not be useful. With that, it brings to an end of the simple linear regression. Now we will look at how to model with one response and multiple explanatory variable. This type of linear regression is called multiple linear regression. We can ask the following question. Does height of a tree depend on its type and its girth? In this case, the explanatory variable x becomes type and girth, and the response variable y becomes height. To visualize the regression lines for multiple categorical variables, we can use geom parallel slopes function from the modern dive package. When you want to run multiple regression model, you will have to separate each explanatory variable using a plus symbol. To run a linear regression as before, we use the lm function. In the formula, we specify log10_height on the left side and log10_girth plus type plus 0 on the right hand side. For the data argument, we specify conifers. We now save it in the conifer model 3 variable. When we run the tidy function on the model object, we see that it returns 5 coefficients. 1 for the log10_girth, and the rest are the different types of conifer trees. The log10_girth is the slope coefficient, and there are 4 intercept for each category of conifer trees. Let's make some predictions. As we have seen before, for predictions, we need to put our new data in a table or a data frame. In this case, we have 2 explanatory variables, type and girth. So we need to make a table that contains 2 columns, one with the type values and the other one with the girth values. The expand grid function from the dplyr package is really helpful here. It returns all combinations of its inputs. Since we have used log10 transform data in our model, we have to convert the girth data to its log10 values. We have done this by using the mutate function from the dplyr package and added log10 transformed girth values to a new column called log10_girth. Finally, we have used the predict function to predict the log10 heights of the trees in our input data. We have also raised these values to its power of 10 to calculate their final heights in feet. With this, we come to an end of the multiple regression part of the course. In the last part of this course, we're going to evaluate our models and look at how good the models are. Previously, we ran 3 linear regression models. The first one was a simple linear regression which looked at one response variable, height, and one explanatory variable, girth. The second one is another simple linear regression model that looked at a categorical explanatory variable. And the third one looked at 2 explanatory variables. One was categorical, the type of tree, and the other one was numeric, the tree girths. So, which model is a better one? There are several metrics that can be used to quantify a model. Let's look at them one by one. The first one is called the coefficient of determination, or R-squared. R-squared is a statistical measure that represents the proportion of variance in the response variable that can be explained by the explanatory variables in the regression model. It is a measure of how well a regression model fits its data. R-squared takes a value between 0 and 1. A value of 1 signifies perfect fit, and a value of 0 means that there is no fit. For simple linear regression, the coefficient of determination can be easily calculated by taking the square of the correlation coefficient of the 2 variables. However, for multiple linear regression, you need to calculate the adjusted coefficient of determination, or adjusted R-squared. What happens is, every time one adds an independent variable to their model, the R-squared values increase whether or not the variable has any significant effect. Adjusted R-squared calculates only increases if the added variable improved the model more than what it was expected by chance. If an explanatory variable does not significantly improve the model, adjusted R-squared value will decrease. It is considered a better measure for comparing models with different numbers of explanatory variables and identifying which variables are truly important. R-squared tends to overestimate the model fit, while adjusted R-squared provides a more conservative estimate. If you're interested, here is the formula to calculate the adjusted R-squared. To keep it simple, we will not go into the details. The summary function prints, among other parameters, the R-squared values. Calling the summary function on the conifer_model object that models height versus girth, we can see that it has an R-squared value of 0.41. The glance function from the broom package can be used to pull the R-squared values. Simply call the glance function with the model object and use the function pull from the dplyr package to extract the adjusted R-squared values. Looking at these values, we see that conifer_model that models girth versus height has the lowest R-squared value of 0.412, and model 3, which takes into account both the girth and type of the tree, has the highest R-squared value of 0.99. Thus, based on the R-squared parameter, we can say that model 3 is the best model. The residual standard error, also known as sigma in linear regression, is the measure of how well the regression line fits the actual data points. It tells you, on average, how far off the model's predictions are from the observed values. The residual standard error takes all the residuals, squares them, then divides them by the degrees of freedom, and then takes the square root. The smaller the residual standard error, the closer the data points are to the fitted regression line on average, meaning that the model fits the data well. A higher residual standard error means that the data points are more spread out around the regression line. The units of the residual standard error are the same as the units of the response variable. Therefore, in the conifer's data, the unit of RSE, or residual standard error, is feet. The glance function in the broom package can be used to pull the RAC or sigma values. Simply call the glance function with the model object and use the function pull from the dplyr package to extract sigma. Looking at the values, we can see that the conifer underscore model that models girth versus height has the highest sigma value of 0.231 feet. And model 3, which takes into account both girth and type, has the lowest sigma value of 0.055 feet. Thus, based on the sigma value parameter, we can say that model 3 is the best model. Instead of looking at values, we can generate some plots that will help us visualize and quantify our model. To make these plots, we will need the GG45 package. Once you have installed and loaded the package, you can use the autoplot function to create several plots. The autoplot function takes the model object and another argument called which that will specify the plot you want to make. Let's look at some of these plots one by one. If a linear regression model is a good fit, then the residuals are approximately normally distributed with a mean of 0. To help us visualize this, we can make a residuals versus fitted plot. To make this plot, call the autoplot argument with the model object and specify the value 1 to the which argument. If residuals met the assumption that they are normally distributed with a mean 0, then the trend line should closely follow y equals 0 line on the plot. When we compare the conifer underscore model to the conifer underscore model underscore 3, we can see that the latter closely follows the line, which makes it a better model. The second diagnostic plot is called a QQ plot. It can be produced by setting the which argument to 2. It also shows whether or not the residuals follow a normal distribution. On the x-axis, the points are the quantiles from a normal distribution. On the y-axis, you get the standardized residuals, which are the residuals divided by the standard deviation. Interpreting this plot is easy. If the points follow the straight diagonal line, they are normally distributed. If not, they are not normally distributed. Here, most of the conifer underscore model underscore 3 data follows the diagonal line closely compared to the first model, conifer underscore model. If you look at the conifer underscore model's QQ plot, you will see that the points deviate from the diagonal line towards the lower end and the higher end. This means that the model is a particularly poor fit for longer heights and shorter height conifer trees. Before moving to the final part of the lesson, let's understand outliers. An outlier is a data point that is significantly different from other values. Outliers can be much larger or much smaller than the majority of the data points. Since these values are significantly different, they can have a huge impact on the model. Let's take a look at the birch data from the conifers dataset. The points in the box plot are the outliers. Since the conifers data is huge, containing 2,500 observations for each type of tree, we will take a smaller sample and explain how the outliers affect the linear regression. You can access this data that contains a small sample of observations for the birch trees from the video description, just like the full conifers dataset. When we look at the scatter plot of the data, we can see that there are a few weird points. These are the outliers for this data. There are two kinds of outliers. The first kind of outlier is when you have an explanatory variable that are extreme. In simple linear regression model, these are easy to find and visualize. You can see that there are two trees, one with a bigger girth and the other one has a smaller girth. These type of extreme explanatory values can be quantified using a parameter called leverage. Leverage measures how far the values of the explanatory variable are from the mean values of those variables. The leverage values can be retrieved by calling a function called hat values on the model object. We have created a new model called birch underscore model on the sample birch data. Calling hat values on the birch model gives its leverage values. Alternatively, we can call a function augment from the broom package to print several parameters, including the hat values. The column .hat, which contains the hat values, can be arranged in a descending order to find the observations with extreme explanatory variable values. As you can see, there are two unusual trees with the largest and the shortest girth. The second kind of outlier is when it lies far from the model predictions. Here, there's a really short and thick tree represented by a pink triangle. These type of values, which lie far from the model predictions, can be quantified using a parameter called the influence. The influence values can be retrieved by calling a function cooks.distance on the model object. Calling cooks.distance on the Birch model gives its influence values. Influence measures how much an observation impacts the estimated coefficients and the fitted values of the regression model. To see how influence works, let's remove the most influential tree. Then we draw the usual regression line in blue, but add another regression line in red using the dataset without that unusual tree. You can see that the slope of the line has completely changed just by having one less data point. We can call the function augment from the broom package to print the influence values. The column .cooksd, which contains the influence values, can be arranged in a descending order to find the observations with extreme values that affect the model coefficients. To summarize, before performing linear regression on your data, do an exploratory data analysis. Then run the LM function on your data. Then evaluate the model parameters. And finally, use your best model to do your predictions. With this, we come to an end of this course on linear regression. I hope you have learned something new today. If you loved the video, please like and subscribe to the channel. It helps me a lot. Thank you.